Okay. Hello, everyone. My name is Pierre Gutierrez, and today I'm going to talk about IoT, machine learning, and how to apply these to help prevention in the medical domain. So a few words about me. I'm a senior data scientist at Dataiku. At Dataiku, what we do is we're trying to create the best software platform for data analysts as well as data scientists. If you have any question on that, please come by our booth later. And so, yeah, today what I want to talk about is most of you probably know this diagram adapted from the CRISP methodology. It's basically starting from business understanding to go to a data science workflow through data acquisition, data transformation, preparation, reshaping, then create your machine learning model, evaluate it, and at some point deploy it. And I want to talk about the few differences that you would have if you were working with IoT and not with, let's say, CRM data that you would have if you work with a business company, for example. And so to do that, I will talk about two examples my company worked on. The first one is epilepsy. So probably some of you don't know that 1 to 3% of the population is affected by this condition, and maybe that's because there are several types of epilepsy. The most famous one is actually the least common, the one with the big seizures. More common is the one where you have absence, up to 100 absence per day, with no real physical symptom, but you cannot really concentrate and focus on the task that you have to do. So a lot of money is spent on epilepsy. There are existing treatments, and one of the main problems is that if you want to be diagnosed, you have to go to the hospital and to have symptoms over there, so it can take days to weeks. And the idea is to shorten this diagnosis time. So enters BioSerenity, one of our partners, and Dataiku. Basically, Dataiku provide the software part. BioSerenity provide the hardware with this connected wearable device that will give some data, typically EEG, which is basically measuring the electricity over the brain. So this is an example of measurement that you could have. In blue is normal condition, and if someone has a seizure or a stroke, you will have something like the red part. So actually trying to detect this before it happens can be really useful to prevent these seizures. In the same way, you can find in EEG things such as spikes. Spikes are useful to detect because a person that is diagnosed with epilepsy is more likely to have spikes. So if you can find these, you can probably diagnose a person to be epileptic or not and start the treatment. So the goal of the project is to allow at-home EEG with this wearable device, and so that the person don't have to go to the hospital and detect the spikes automatically, detect the seizure, and of course do the diagnosis. The other example is detecting what people do in their home. The application is that there is a growing number of persons over 60. This number is increasing rapidly. These people tend to live alone, and so when they fall or when they have strokes at their home, they don't have anyone to help them. So if they had wearable device or sensors that could capture the fact that they fall, then we could probably help them. As a matter of fact, it happened to the grandfather of one of my interns. The person fell on the floor, was unable to reach the phone, and spent 24 hours blocked in his house without anyone to be able to help him. So enters the Sphere challenge. It was a data science competition recently. We made a second on this competition, and the idea is really to have wearable tech, sensors such as cameras or infrared, and detect what is the person doing. So they have other objectives from detecting the falls and the strokes, such as analyze the eating behavior, but also see if the person is depressed or if the person has anxiety. So these are the two examples, and now I'm going to start talking about data science. So the first step that you would have to do is start with this acquisition phase, preparation of the data for your machine learning models. So one of the big differences between CRM data or what you can see in the data science books is that when you're dealing with IoT, you are actually sampling something from a continuous signal. So for example, for the epilepsy, what we have is around 24 channels of EEG. You have to choose the sampling frequency, and this will generate a large amount of data that is synchronized by night with Wi-Fi. We store everything on S3. And the idea is really to be able to scale to thousands of patients and several days of data. In the safe aging competition, basically what they ask is for people to go in different rooms and to do some stuff such as lying on the bed, walking, sitting on a chair. And they get all these different measurements from accelerometers, from a bracelet, cameras, bounding box to preserve anonymity, and some other sensors values. So now that we have this data, the need we have for the database and the storage are these ones. First, we need to be able to interpolate easily, because you can have a problem of Wi-Fi synchronization, you can have one of the devices failing, so at some point you will have probably some missing data. And the same idea, you have to have the smart sampling thing, because if you want to have a global view of the time series, you have to be able to downsample, you have to be able to zoom at a precise location in the time series. And also, as I said before here, you have a bunch of different sensors for this application, and this means that probably the frequency are actually not the same. So if you want to do some machine learning modeling at the end, what you need is to be able to join them on the same timestamps. So at this point, you need really to have this interpolation and smart sampling features. And also you need aggregation, because obviously you are going to do rolling averages for feature engineering and so on. So what kind of database can you use? You can think about relational database, such as PostgreSQL or storing things on HDFS, Impala Hive, this kind of stuff. For these, aggregation will be efficient. If you want to join different sensors, as we see on the left, the problem is that you have to actually create first the time series of the timestamp, all the timestamp that you have, and then join everything on top of that. And if you want to do the interpolation, you have to do everything by yourself, so it can lead to a huge amount of time-consuming operation. Even worse, if you store that in MongoDB, as I've seen some company do it, probably because it's more efficient from the app perspective. But once you need to deal with this actual time series, you barely have the aggregation, and then if you want to sample or interpolate things, you basically have to do like huge reprocessings. So the solution we found is to actually use time series as time series. You have these nice databases that are time series oriented, such as InfluxDB, OpenTSDB, and KerosDB. OpenTSDB is based on HBase, Keros, and Cassandra, and I think InfluxDB is the kind of trendy right now for these databases. The cool stuff is that they have all these features so that you can easily work with the time series. And so once you're able to do that, the way we process the data from the EEG or from the different sensors is using Python in memory, because Pandas has also these nice upsampling features, and NumPy and SciPy are very fast for classical transformations, such as doing FFT, creating correlation, and so on. So once you've done all this reshaping, preparation of data, you can start thinking about creating your machine learning model and evaluate it properly. So an example would be for EEG. If you want to detect spikes, what you will do is have some physician, doctor label some of these EEG time series, such as the one that you can see over there. If you have a spike, then you can put a 1. It's a classification problem, rather easy. And then you will sample randomly other timestamps to create the zeros that you need for normal behavior. In the sphere movement detection, it's the same idea. You will have some people that will label what the person is doing, and at the same time, you will have the timestamp, and you can recreate this time series and take that as feature. So when we talk about machine learning, you have to first create your different features. And with this IoT data, you often have two kind of features. The first one is the descriptive ones. You have the electrical medical record, for example, of each patient. You have, in the case of movement detection, you have, of course, the age of the person, his weight, which can really influx what the position of the bracelet and the accelerometers give you. And at the same time, you have all these time series features, which are like based on the current position, previous position, correlation between different time series. If you think about EEG, one very classical feature is to actually check the correlation between each of the probes, each of the time series, and calculate the values of the similarity matrix. All right, if you have done all this transformation, you can actually use simple machine learning models such as logistic regression or random forest. And if you have a lot of data, then you can start not caring at all about this feature engineering part. So for example, for the sphere challenge, where we tried to detect the position, what we did was actually feeding to the model only the previous values of the different accelerometers. We didn't calculate any real features. We let the model infer all of the correlation and interaction between the variables. In the same way, we first started with model for epilepsy using the correlation between the different leads, the different time series. And we ended up having a lot of data. So what we did was use recurrent neural networks in order to predict the different strokes. And when you use these kind of things, you have to understand that you don't do the feature engineering anymore. The network does that for you. But it means that the choice of the network architecture is actually what you would consider your feature engineering. All right, and so one of the most important things in this particular use case is the generalization problem. Because when you have IoT, let's say you have 4 patients and 4 reads. So I have 4 examples for each patient. One of the ways to train and validate my model is to take one of the reads per patient as my validation set. If I do that, my offline performance will be very good. I will have a AUC between 0.9 and 1. And this is because I can, if I see something for a person, I can generalize easily. However, if I wanted to deploy that to a new person, I would have to train on a subset of my person, then validate on the 4th one, and now I see a large drop of performance. I go from 0.9 to 0.7 or 0.8, and it means that I don't really generalize well to a new patient. And this is kind of one of the big worries that we have with IoT and machine learning, is that we have a poor generalization to new people in general, to new device. I mean, if the technology changes, if BioSerenity changes the captors that they are using, it will be a huge problem for us because we will have to transfer part of the knowledge to the new technology. In the same way, all the tags, all what we're trying to predict depends on the physician that annotated. So basically, if we have just 2 physicians, maybe they they can be a bit biased. So we have to get rid of this bias. And so to do that, we need more patients, more doctors, and more device. That's the data way of thinking. Though for now, like having more patients is a bit expensive. In the same way, when we worked on Sphere, we had a generalization to new patient that was good, but everything happened in the same home, in the same controlled experiment, and generalizing this to a new home or to new patient, to new device require some warm start. So you would have to, for example, ask the person to go in the room to annotate for this person, and then to be able to recognize what he will be doing in the future. The problem of that is, of course, that it's very expensive, and you would have to deploy one person for each house, which is not scalable. So the other solution would be, again, to have more patients and more data. And just before concluding, a few words about deploying. A lot of people think that when you're doing IoT, you have to deploy everything in real time, have this real-time learning of the model, real-time scoring. In our use cases, for the epilepsy spike detection, for example, things what you want to do is shorten the time for detection. If you let the person one day with the wearable device during the night, you can actually score everything by batch. So you don't really need to be that fast. However, if you're thinking about the Sphere challenge, where we need to detect right away if a person falls on the floor in order to detect if we need to send help, then in this case, of course, you have to do real-time scoring. And this is a bit more problematic because in this kind of challenge, like Kaggle challenge, people tend to do like very big ensembles in order to win the competition. And this would not work in this kind of case because the processing time would start to be too big. And so yes, in practice, for the deployment of the thing, as I said before, one of the problems is the generalization. So one of the real challenge now is to go from a clinical experiment where everything is controlled to the real world where the device can be wrongly set, where some people, instead of putting the bracelet on their right hand, just put that on the left hand, and you still have to cope with this kind of thing. All right, and so to conclude, from our perspective at Dataiku, the new explosion of IoT device will really help the medicine world with the prevention, early detection, and diagnosis of different conditions. They produce a lot of data, so you really have to focus on the new technology that's out there in order to work with them. The data science workflow that people actually use for other things is still possible to apply, even if there are some differences. And yeah, the real conclusion is that a lot of stuff works really well in controlled experiments, offline evaluation, and so on. But we have a lot of trouble actually deploying that in real life. Right. So that was my talk. Thank you for your attention.